Hi everyone, I am Dr. Subbarao from RVIT Institute of Technology. In this video, I am going to explain extrinsic semiconductors and the classification of extrinsic semiconductors. The first one we have to know what are extrinsic semiconductors. Extrinsic semiconductors are the materials which are formed by the doping of impurities. For example, boron, phosphorus, arsenic, bismuth. These are the impurities added to the pure semiconducting materials. So the extrinsic semiconductor is a pure semiconductor like silicon or germanium that has been doped with a small amount of impurities to improve its electrical conductivity. So those are the extrinsic semiconductors. An extrinsic semiconductor is a semiconductor whose electrical conductivity has been enhanced by adding some impurities. That means a intrinsic semiconductor having some conductivity. If we want to enhance the conductance of that material, that means either it may be increased or may be decreased. We can add some of the impurities. Based upon the added impurities, the process of addition is the doping process and the impurities are doped impurities. The doped impurities properties will affect the conductance of the intrinsic semiconductors. That's why the conductance of the intrinsic semiconductors changed and they form the extrinsic semiconductors with new properties. Now, the impurities provided the extra holes or electrons to conduct the electricity. And what is the doping? Doping is the process of adding small amount of impurities to the pure form of the semiconductor in order to increase the electrical conductivity. So this is the process is called doping. Now coming to the classification of extrinsic semiconductors. By depending upon the impurities were added to the intrinsic semiconductor, these are classified into two types. The first one is the P-type semiconductors and second one is the N-type semiconductors. Here extrinsic semiconductors are the impure conductors. Here these are the two types, P-type semiconductors and N-type semiconductors. Coming to the P-type semiconductors, these are formed by the addition of trivalent impurities. Trivalent means the valency of the materials is equals to the 3. So if we added trivalent impurities to the pure semiconducting materials, they give P-type semiconductors. For example, boron doped silicon. Boron have the valency 3 and aluminum doped silicon. Aluminum having the valency 3 and boron doped germanium. So silicon is the intrinsic semiconductor having the pure silicon atoms and germanium is also pure intrinsic semiconductor having the germanium atoms. If we are adding boron atoms to the silicon material, that's mean the process of addition of trivalent impurities to the pure semiconducting material. Then only the P-type semiconductors were formed. That is the boron doped silicon P-type semiconductor. And coming to the N-type semiconductors, here the pure intrinsic semiconductors were doped by pentavalent impurities. So here the pentavalent impurities means the valency of the atoms having the 5. That means 5 unpaired electrons or 5 valency electrons present in N-type semiconducting materials. So these are the impurities added to the pure intrinsic semiconducting materials. For example, silicon doped with phosphorus and germanium doped with phosphorus. So these are the examples of our N-type semiconductors. Now coming to the first one, P-type semiconductors. So we already know P-type semiconductors were formed by the addition of trivalent impurities. So the process of addition of trivalent impurities to the pure semiconducting material. We got the P-type semiconductors. Here the trivalent impurities boron, aluminum or gallium. These are the trivalent impurities having the valency 3. For example, boron doped silicon semiconductor. So silicon conductor already we discussed in the previous videos. Here we are doping the boron trivalent impurity to the pure silicon conducting material. Silicon have the valency 4 and each silicon attached by 4 other silicon atoms and forms the covalent bond. Here boron, the atomic number of boron atom is 5 and the electronic configuration of boron atom is equals to helium 2s2 2p1. This is the valency electronic configuration of boron, the outer electronic configuration. So this 2s2 having the 2 electrons and 2p1, that means p orbital having the 1 electron in 2pz orbital. Now this boron atom absorbs some part of energy, then the electron is excited. Hence, the electron present in the 2s orbital will comes out and enter into the 2py orbital. So this is the excited electronic configuration of boron atom. Helium 2s1, 2p2. That means the electron present in s orbital is enter into the 2py orbital. So this is the excited electronic configuration of boron atom. The first electron enter into the 2s orbital and the second electron enter into the 2pz orbital and the third electron enter into the 2py orbital. This is the electron filling in the excited boron atom. Here the valency electron, how many valency electrons are there? So this boron having the 3 valency electrons. And what about this 2px? This 2px is the empty orbital. Empty means this is the creating hole. The empty orbital means the orbital which are not having any single electrons are called the empty orbitals. These are the vacant orbital, empty or vacant orbital. This empty orbital or vacant orbitals creates holes. So this is the boron atom. Boron atom having three electrons. These are the 3 unpaired electrons. And one hole. Hole is the representation of this vacant orbital. Now, this boron is added to the pure silicon. This is the pure silicon. Now, this boron is surrounded by 4 silicon atoms. Each silicon atom contribute 1 electron. But here boron contribute 3 electrons and 1 hole. This empty is the free hole. Due to the presence of a free hole, this semiconductor conduct electricity. So the majority charge carriers in p-type semiconductors are holes. So due to the formation of holes within the p-type semiconductors, they conduct the electricity. Now the formation of p-type semiconductors, how they formed. So the p-type semiconductors having the boron doped with pure silicon intrinsic semiconducting material. Here boron having 3 unpaired electrons and 1 vacant orbital. So this is the vacant orbital creates a hole. This is the 1 hole shared with 1 silicon atom and the remaining 3 electrons shared with 3 other silicon atoms. They forms the strong covalent bonds. So this is the boron atom. 1 silicon atom contribute 1 electron and boron atom contribute 1 electron. Here there is a formation of a covalent bond. And here another silicon forms the another covalent bond with the boron atom. And next another silicon atom forms the third electron containing the third electron present in the valency of the boron and forms a covalent bond. Here there is only one free hole. This hole is shared by the another silicon and forms the covalent bond. This is the why each silicon is further bonded with the other three silicons because already it bonded with the boron. So remaining 3 electrons shared with three other silicon atoms and forms the covalent bonds. This is the formation of p-type semiconductors. Boron doped silicon semiconductor. Here this boron having the hole. This is the conduction hole. Due to the presence of conduction hole, they conduct the electricity. Now coming to the conduction. How the electric current flows through the p-type semiconducting material. If you see here, this is the p-type semiconductor. This conductor is connected to the external battery. That means one end of the semiconductor is connected to the negative terminal of the battery and another end is connected to the positive end of the battery. Here, this these two plates, one is small and another one is larger. So this large plate indication of positive charge and this smaller plate indication of negative charge. This positive charge creates the holes. So here the majority charge carriers in p-type semiconductors are holes. So the holes are transmitted from the positive terminal of the battery and enter into the semiconducting material. And here the electrons flows to the opposite to the holes direction. That means holes are moving in forward direction, then the electrons are moving in backward direction. That's why they conduct the electricity. Here coming to the valency band and conduction band. So valency band have the electrons and conduction band, this valency band have the holes and conduction band have the electrons. And the electrons are coming from conduction band to the valency band. Next one, applications of p-type semiconductors. These p-type semiconductors are widely used in diodes and transistor fabrications. So for diodes, the p-type semiconductors are the key parts of diodes, which are essential for converting alternate current to direct current. It also play a role in signal detection. That means diodes are the electric materials which convert the alternate current into direct current. So all the computer or electronic devices having the electronic circuits, all the materials were using the DC current, but we are supplying the alternate current. Here these diodes convert this alternate current into direct current. For this conversion, we are using the p-type semiconductors. And next one, transistors. These transistors were formed by the combination of p-type semiconductors and n-type conductors. So they forms the junction, that means a p-n junction or n-p junction. So due to the presence of that junctions, they conduct the electricity. Here, these are used for the amplification and switching process. And next one is the integrated circuits. All electronic devices having the integrated circuits. Those integrated circuits were synthesized, were fabricated by using the p-type semiconductors. And the next one, solar cells. So by increase the conductivity of the solar panels, we are introduced to the p-type semiconductors and also this combined with the n-type semiconductors to form the junction, p-n junction, which is very essential for the solar cells. So the movement of holes in the p-type semiconductor and the movement of electrons in the n-type semiconductors, they conduct the electricity. And the next one, the light emitting diodes, LEDs. LEDs were fabricated by using the p-type semiconductors. So these convert the electrical energy into light energy. And next one, photo detectors, the radiation detectors. So the radiation detectors are also fabricated by using the p-type semiconductors. So these detectors here, these converted the light into the electrical signals. Whenever the light energy is incident on the photoelectric detector, so it converted the electrical signals. And some other applications I'm showing here. First one is the sensors. P-type semiconductors are used to fabricate these sensors. For example, temperature sensors and radiation sensors. And the next one is the automotive devices. They are used in automotive devices and electronics and wireless communication equipment. So the P-type semiconductors are widely used in integrated circuits for wireless communication. Next one is the interface bridge ICs. So they are used in interface bridge ICs for mobile peripherals devices. So these are the examples. These are the applications of P-type semiconducting materials. Thanks for watching. If you like this video, please like, share, subscribe, and please click the bell icon symbol for more informative videos. Thank you.